Hey everybody, Corey and Victoria here. We are the Professors DuBois, and we're going to continue our topic of thermochemistry, specifically with the energy of chemical reactions today.
Yeah, so far we've really talked about how heat can be transferred between objects, how heat can change the phase of something, but really what we want to get really into is the heat and the energy involved in chemical change or chemical reactions.
So we talked before about internal energy representing the total energy of a chemical system. This is kinetic and potential. Well, there's a new term, enthalpy, which is a thermodynamic quantity that allows us to study the heat exchange in these reactions. And it's really defined as the sum of the internal energy of a system plus the product of pressure and volume.
Yeah, so these reactions that we're going to be talking about are typically performed at constant pressure, which means no work is being done. So under these conditions, our change in enthalpy is the same as our Q, the same Q that we've been talking about, which is the heat transferred.
Now, enthalpy is related to both the potential energy and the degree to which the electrons are attracted to the nucleus. So if there's a strong attraction, we'll have strong bonds, and these molecules are stable and enthalpy is low. Now, weak attraction between electrons and nuclei results in weak bonds, which are relatively unstable, and enthalpy is high.
So do chemical bonds contain energy? And this may be a little bit counterintuitive. So you might be thinking, okay, a stronger bond, more energy, and that's not the case. So the presence of strong bonds does not correlate with a large degree of stored potential energy. And in fact, where bonds are formed, where a chemical state where bonds could be formed but aren't yet, is where we have high potential energy. So it's almost like the potential for this bond. And once the bond is formed, the energy is actually released, and you have a lower enthalpy in that bonded state.
So our changes in enthalpy can either be endothermic or exothermic, just like we saw with energy or heat, Q, and the same rules apply. So if we're endothermic, that's saying that heat is flowing from the surroundings to the system. If we're exothermic, that extra energy is going from the system to the surroundings. So the surroundings would get warmer. Now this change in enthalpy is we do it just like the change in temperature. Final enthalpy minus the initial enthalpy.
So now we're talking about the reaction, right? We're not just talking about the enthalpy of a substance with its bonds, but the change in enthalpy from products to reactants or reactants to products.
And just like Q or heat, the sign is just telling us the direction of the heat flow. So for those endothermic chemical reactions, the delta H would be greater than 0, whereas an exothermic would have a delta H at negative or less than 0.
Yeah. So an exothermic process. So just kind of a recap here. So heat is transferred from the system to the surroundings, exiting. The enthalpy change has a negative value. Negative delta H means exothermic. And weakly bonded molecules must be being converted to strongly bonded molecules. And that's the change that's happening between products and reactants.
And just to go through the same thing with the endothermic process. So the heat transfer from surroundings to the system. The enthalpy change has a positive value, just means delta H is going to be positive, greater than 0. And in this case, we have strongly bonded molecules that are being converted to weakly bonded molecules. So heat is converted into potential energy, and the temperature of the surroundings decreases.
Okay, so we can represent these with something called an enthalpy diagram or a potential energy diagram, and we like these because we like to be able to visualize what's going on. So if your reactants are of higher enthalpy or higher energy than your products, then your delta H has gone down. So we have a negative delta H. So this is representing an exothermic reaction. So your products are lower than your reactants.
And if you look on this graph here on this chart, it says enthalpy on the y-axis, and we're just showing on the x-axis the the reaction progress. So we're starting with reactants and we're going to products as we move left to right. So if we had values
It's almost like time.
If we had values on that y-axis, we could actually calculate a number, but you can see from this diagram that the value for the products is smaller than the value for the reactants. And to get the delta H, we go products minus reactants. So this is going to be a small value minus a large value, and that's going to be negative.
End up with negative for sure.
So an endothermic diagram looks like this. Our products now have higher enthalpy than our reactants. If we do a delta H, products minus reactants, we're going to have a positive value.
So increase in energy. So there's 3 different types of enthalpy that you might be running across in your calculations, and you might see heat of reaction, standard molar enthalpy, and the enthalpy of formation. And they do all represent enthalpy, changes in enthalpy, but they're very different. So the heat of reaction is the heat that's given off or taken in for a reaction the way that it's written, and in the molar quantities that it's written in. The standard molar enthalpy is if 1 mole of substance reacts, and it may not be written like that in your balanced equation. The enthalpy of formation is something that we can only measure the change in enthalpy, and the change in enthalpy from its elements to form a compound. That difference is your enthalpy of formation. So from its elements to form a compound, the enthalpy of formation of that compound is the difference between the two. And it's 1 mole as well.
And we're going to get into that in detail, actually. We're going to spend some time on that.
We'll cover all of these.
So we're going to start with this enthalpy for the reaction. And just like a regular chemical equation, we can put our energy into the equation as like a term. So this equation at the top, CH4 plus the 2O2, it has a delta H value given. It's negative. That means it's exothermic, 802 kilojoules. Well, I could write that in the equation as a product, as we've seen here. So now we actually have some conversion factors. We can tell the relationship. We can do stoichiometry using energy values. So we know the moles of each, and we know the amount of energy. So we can say that there's 802 kilojoules of energy released for every 1 mole of CH4 consumed, or for every 2 moles of H2O produced. So you could be given a question where you might have to determine, based on a reaction like this, determine the amount of energy if you had grams of CH4. You might have to convert grams to moles and then use this factor.
Let's show you an example. All right. How many kilojoules of energy are released when, so we have an exothermic process here, when this many grams of methane are burned? So we're going to burn methane. We need a balanced equation, and we have one here, but you could certainly have produced this yourself. And we have our mole-to-mole ratios of our substances here, but we also can add in our energy term now. So it's negative. Negative means exothermic. Negative means being produced. It's a product. And we can put this on this side. It's a positive because it's an actual energy here. The negative just means that it goes on the product side. So we have some conversion factors now. And that's kind of the way that we want you to recognize that you have this conversion factor here in red. So now there's a negative, or an amount of 802 kilojoules that would be given off. That's what the negative means, for 1 mole of methane burned, because that was the heat of reaction. Delta H of reaction is as this equation is written, which means that for every 1 mole of methane burned, you're going to give off 802 kilojoules. So we have our conversion factor is in moles. We have to go from grams to moles first, which is our first step here. And then we can use this as our conversion factor.
Now, the fact that they asked how many kilojoules of energy are released, I don't believe you'd have to put the negative in here. I think they just want the magnitude. And again, I can't emphasize this enough. All that sign means is the direction of the heat flow. So I wouldn't mark this as incorrect, but it would probably be more correct just to give the value.
if you write the words, this many kilojoules were released, then that also then indicates the direction. It's the same as saying negative.
All right, so we've got one for you to give a try.
Yeah, practice.
Provided the equation, double check that that's balanced, and we gave you the standard molar enthalpy value, and so I would write that into my equation, and it says, what is the heat change? Okay, this time I think you do want the negative, because we want to know, is the heat change, what direction is that? So
another point is this is saying this is the standard molar enthalpy. So that means that it would be for 1 mole of propane, but that's the way this is written anyway. So it ends up being the same. So the heat of reaction is the same as the standard molar enthalpy in this example, as long as we were at standard conditions.
Okay, and there is your answer. So this time we do add the negative to show that that is an exothermic reaction. It's a combustion reaction, so we're burning propane. We would expect this to be an exothermic, and that value's pretty big, but it's probably not surprising. That's considering
why we use it for fuel.
Exactly. Exactly. All right, so that sums up our introduction to enthalpy. Hope you enjoyed it. We appreciate you watching, and stay tuned. More to come in thermochemistry.
Bye-bye.